my this is action S phi. So, how do I compute S phi is so this e to the power minus beta h beta s sorry beta s is integral of free energy for statistical field theory. I need to do the integral d phi. So, you have to go to field theory. So, we have let us say spin variables, okay, magnetization. So, spin variables, then I will construct the Hamiltonian. Hamiltonian will be okay. We constructed Hamiltonian for some like phi 4 theory. So, it is phi squared, in front is let us say called r, then c grad phi squared. Hamiltonian, this is a density, Hamiltonian density. Then we have a nonlinear term, which I will write as u phi 4 by factorial 4. So, factorial 4 will I will tell you why we do it. So, that is a notation people use it, okay. So, 4 will cancel with 4 and you get u by 6, the half will cancel with this 2 when I take the derivative, okay, and this is a normal convention of Hamiltonian density. If I integrate this Hamiltonian density or free energy, okay, free energy and Hamiltonian density will keep it same interchangeably in this course. So, if I take the sum over all field full space, then I will get a number Hamiltonian total energy, right, or if it is free energy F, then I take free energy and integrate over this, then I will get S, okay. This is a effective action, alright. So, this effective action is coming here, okay. So, when you say e to the power minus beta h, this h is the total Hamiltonian or total energy, no, and that is what you studied, no, and if you are putting in a heat bath, then basically total free energy goes in there. Had it been isolated system, then you put energy, otherwise you put a free energy, okay. So, this what I will S phi will be there. Now, please keep in mind that exponential of a number of an object, this must be a non-dimensional number, action is a non-dimensional number, okay. So, we have h, but I divide this by beta, right, h by kbt. H by kbt is a non-dimensional number, exponential of 1 centimeter does not make any sense, but we will make beta as 1. So, all the dimensions are absorbed in C. So, I am going to put beta as 1 here. So, I will say S phi is dimensionless, okay. We will need this idea in a coming discussion, okay. Now, you may recall that these are the linear terms, phi squared and grad phi squared is a linear term. If I take the derivative to get equation of state or not equation of motion, then I will get terms linear in phi and linear in derivatives of phi, okay. So, in fact, we can write down equation for this, we did that d by dt, in fact, it was a double derivative, double derivative of phi minus Laplacian of phi, right. The right hand side was phi, this was my equation, and r is coming here as, in fact, that was m squared phi, r is same like r is m squared, I wrote m squared mass squared in the previous discussion, r is like r is in fact m squared, I am not sure about the sign, is a minus or plus, but we will ignore it for time being, okay. This is a linear equation in phi, but what happens to phi 4? If I take derivative of this with phi, then I will get phi cube. So, this term will give us plus u by 6 phi cube, yes, this is the term. Now, is it linear or non-linear? Phi cube is non-linear, okay, and that is going to cause trouble, okay. That is what we need to compute I have total magnetization when phi cube term is present, okay, and that is where the problem will start coming in. So, I am going to put this S phi a sum of two parts, the free part or linear part and non-linear part. So, we call it, this is called free part and this is called interacting part. Okay. Now, why is it called interaction? Now, this is so without phi cube this is a linear, this is a free field, right. Why is it called free field? Because if I take the Fourier transforms, then I can write down equation for each Fourier mode, okay, correct. So, there will be a equation for each Fourier mode which will be d dt minus k squared equal plus phi k equal to r phi k, right. In fact, I can solve it analytically, correct. Now, what, so this is each phi k is evolving separately, right, there is no interaction, each phi k is a wave, they are just moving along. But as soon as I put phi cube, then what will happen? Did we discuss it in the class? I am not sure. See, if I put a phi cube, then it will, so I am doing a Fourier transform of this object, left hand side and right hand side, okay. So, Fourier transform of left hand side will give you this, so Laplacian gives you k squared. What happens Fourier transform of r phi is going to be r phi k. Fourier transform of a product, what is Fourier transform of a product? Is a convolution. So, what will this convolution will be? U is a number, huh? So, is u by 6. So, phi cube will be product of a convolution of 3 phi k's. So, we write this as phi k1, phi k2, phi k3 such that k1 plus k2 plus k3 equal to k, okay. So, this is the term, these are all Fourier. Now, you can see that these Fourier modes are interacting with each other, right. Phi k1, phi k2, phi k3 is interacting with each other, and that is why this is called interaction, okay, among the Fourier modes. And so, it is a called quartic interaction. So, if I represent this in terms of waves, what will I get? So, there is a wave number k and it is equal to k1 plus k2 plus k3. I am not writing in the vector stuff, is k1, k2, k3, k1, k2, k3. So, the 4 waves are interacting, and that is called quartic interaction. Okay. So, this is interaction term. Now, connecting these to spins, I have one slide. So, right now let me just say this. So, we have spins, no, sitting on a lattice sites, Ising spins like that, up down, or it could be a vector, you know. So, that is a Heisenberg spin if it is rotating. Now, we can write down Hamiltonian as h times spin sigma dot b, right. So, h dot sigma minus h dot sigma, that is b dot sigma, let us write b dot sigma, okay, that is Hamiltonian. Hamiltonian is a, so I do not want to confuse with h, which is Hamiltonian, and the magnetic field h, okay. In our discussion we will involve magnetic field a small h, okay. So, b dot sigma, let us call it b dot sigma, dot product, huh? Will it be linear or non-linear? If my Hamiltonian is b dot sigma, and is it a linear term or non-linear term? So, linear term we can, okay. So, this is a linear in sigma. So, there is no interaction among the spins. This is not looking like that, this is for fields, this is for like spin at the sites. Now, we can bring in interaction among the spins, which is j sigma I sigma j, sum over I sum over j, right. That is what you write interactions. Well, it could be local interaction, mostly local interactions. Now, this is called interaction term, which is between neighbors. Now, it turns out which we will not do in this course, that these interactions lead to term of 5-4 type. So, this corresponds to these guys and these guys have connections. Okay. Now, which we will not discuss, but nonlinearity phi cube is in fact, or phi 4 in Hamiltonian is coming from this sigma I sigma j. Okay. This is done by a lot of stalwarts, like the name which will come soon is Ken Wilson, okay, and the people who derived kind of phi 4s from here. Okay. So, that discussion we will not do. So, I hope this part is clear, that we need interactions for bringing in more complicated or more interesting phenomena. Okay. Now, how do I compute partition function with S interaction inside? Okay. Now, the linear part is quadratic, phi k phi minus k, right. In fact, when you do this partition function, integral d phi exponential minus beta by 2 sum e k phi minus k, this is can be written in terms of matrix, no, a x transpose a x. This can be written as a thing which I showed in the previous slides. But when I have interactions which is not just products of two variables, but product of 4 variables. Now, this is for phi cube, but phi 4 I did not write it. What is for phi 4? If I want to Fourier transform phi 4, I have 4 phi's sitting here in the Hamiltonian. Okay. In the equation of motion, I have 1 phi k, but corresponding term in the Hamiltonian is product phi k phi minus k, right. Phi squared is, so we can write down the energy Hamiltonian in Fourier space. Okay, like that. So, this will be R phi k phi minus k, this is the first term. Second term will be this half sitting here. Second term will be C k squared phi k phi minus k, and the phi 4 will be involved what? Plus 4 sums. Well, I should put the sum here. Total energy, no, sum over all. So, it is a, here it will be phi k1, phi k2, phi k3, phi k4, and there is a u sitting there, and such that k1 plus k2 plus k3 plus k4 is 0, and I have to sum over all possible k's. Okay. So, this involves 4 phi's, so e to the power minus beta, well, I mean not u, there is a u sitting here, there is a u by and there is sum of 4 of this, and that cannot be written as x transpose a x, right, because 4 quadratic will be only 2 phi's. This object cannot be written in the form x transpose a x, right, this cannot be written, and that is a big problem. So, computing this partition function with interaction, S interaction is like that, okay, and so that is that's the issue. I hope everybody is clear. So, I cannot compute it analytically. Okay. So, bringing in interaction is a problem. So, how do I do it? And this where the perturbative expansion will come. So, this E exponential minus S interaction, I start putting them as a series sum. Okay. So, this is Taylor series, the minus sign. So, minus 1 to the power nu by nu factorial S interaction to the power nu is going from 0 to infinity, it is just Taylor series. Okay. S interaction is a set, this is a number. of course function of phi, but it is a number. Now, what is this object by the way? I am not dividing by z naught, but this is expectation value. Well, if I do the normalization part, so remember what was d phi, any function phi exponential minus s naught phi. What is this? This is, there is n sitting there, normalization. This is average value of f phi. Okay. So, this is basically average value of S interaction with normalization. I had to dump in the organization normalization. So, okay. Now, normalization is basically the inverse of the free partition function. Everybody is with me or not? Right. So, this normalization, as I showed you, was inverse of this thing. So, that is the free partition function. This is with no interaction. This is the z naught is a partition function with no interaction, and this partition function with interaction. Okay, partition function, this full partition function. Okay. Now, so z by z naught. So, in fact, I was telling you here is I need to divide by z naught to get this this stuff. So, this thing will keep appearing z by z naught, and I am do some bit of hand waving because to put all the derivation in the PPT is bit lengthy. So, I just wrote that. So, in fact, this n is 1 by z naught. Okay, that is what is coming here.